Hello, let's discuss radians and degrees. So first of all, why do we use radians? Radians are used very widely in physics and engineering and math. So why do we use radians instead of degrees? I know that you're probably more used to degrees than radians. And that's the same for me. I'm more used to degrees, and sometimes I would say, oh, that thing is 90 degrees from the other, instead of saying that thing is perpendicular to this thing. Okay, so there are some reasons for using radians. First of all, this degree is completely a human construct. So we say 360 degrees is equal to one revolution. Okay, so one circle, right? So one revolution could be pretty universal, and we could observe any planets orbiting a star, right? So 360, this number is completely magical. You could also say 400 if you want. In reality, there is a gradient, Gradian. So 400 gradients. And you can make your own definition if you want, 1,000 something, right? Make it up. So this number here, or that number over there, completely made up. It's just a human construct. It's convention. And comparing to those, we say that 2 pi radians is equal to 1 revolution. And that is actually universal. This factor here is a factor that relates to the circumference. So circumference of a circle, which is 2 times pi times r, and the radius, which is r, right? So circumference versus radius. This is a universal fraction. And if we're using this to define angles, it'll be universal compared to what these arbitrary numbers are. So let's take a look at the definition here. How do we define, say, 1 radian? I usually do this 57.3 degrees because we know what that is. This is a little less than 60 degrees, and we also know what that is. 60 degrees equilateral triangle. Okay, so 60, 60, 60, right? We know that. What if we just made all these into radius? So we move on to the left side. This is a radius r, and this black line radius r, this black line radius r. Okay, so we have 60 degrees from this horizontal black line to this angled black line, 60 degrees. And what if we take this r here and we bend it into this arc? Well, because it's curved, it's not going to reach as far as this straight R, so it's only going to reach over here, this red arc. So the angle the red makes with this horizontal black is a little less than the 60 degree angle, and it is 57.3 degrees. So this is how the two units are comparing against each other. A radian is close enough to 60 degrees, but a little less because 60 degrees requires this straight R, and 1 radian is this R that is curved, so it doesn't reach as far. And then you imagine 360 degrees, right? So that is 6 of these things, and each one is slightly more than 1 radian. So if you add them all together, so a full circle of revolution is a little more than 6 radians, so 6.28, right? So a radian, for definition, this is just comparison. So a radian is defined as a length over another length. So this is the arc length, and this is the radial length. Alright, so let's get back to the left side. So this is the arc length. If you make a fraction between this length and this length, or this red line, and you find out they're 1-to-1 ratio, then you find the angle being 1 radian. So if you keep going, if you get a little longer, say maybe twice as long as the that 1 r, so you get 2 r's. Maybe you get over here this whole thing. This is an r, the red portion, and then it follows along. This is another r, and then this angle here will be 2 radians. All right, so 2 radians, and you just keep going, and it'll be a little less than the 180 degrees, since we said each 60 degrees is a little more than 1 radian. So there's another radian, right? So this is another radian. This is 2. This is 1 radian, and you keep going, and here's another r. Here's another 1 radian. Here's another r, arc length, and another 1 radian. And then you get over here, this is another r and another radian, so 1 radian. So you got 1, 2, 3, 4, 5, 6, and there's a little bit left, 0.28 radians. Right. So that's how you express an angle in terms of an arc length divided by this radial length. Okay, so what is the advantage of using this? Besides, we have this universal factor of pi. That is awesome, but does it actually make anything easier? The answer is it does. It makes things easier. So let's take a look at one example to figure out a length on our arc from the angle. So let's just say we still have this situation, but now we're trying to describe something that's moving along a circle. This could be just a sling, right? Just going around the shot on the sling, going around a circle. It could be a planet going around a star. So now it's going around a circle, and we want to find out the relationship between the angular velocity and the linear velocity. So the angular velocity, let's say angular velocity omega, is approximately equal to the change of angle over the duration of time that change happened. So this angle here, we can use angle in radians, and then over time, right? So what about velocity? Okay, so if I just draw a diagram here, let's imagine we start from this angle. Here's the center, and we travel up. So this is our delta angle, and we spent delta t just trying to cover that angle, and this arc has a length of delta s. So now we want to find out the velocity, the linear velocity. We know that must be delta s, the length, over delta t. Alright, so because we're using radians, this angle delta theta is going to be arc length, right? So back here, arc length over radial length. And what is arc length? Delta s, right? Arc length. And here, let's have an r there over radial length of r. So this means that omega, which is delta theta over delta t, is equal to delta s over r over delta t. If you rearrange the terms a little bit, 1 over r, delta s over delta t. So this is velocity, v over r, or v equals omega r. So that is something you're probably familiar with, right? So in a uniform circular motion, or in trying to relate a linear velocity with an angular velocity, v equals omega r. So this makes it convenient, especially in mechanics. So that concerns physics and maybe mechanical engineering, even electrical engineering, if you're thinking about controlling vehicles or anything that rotates, even machines. So what if you used a degree in angle? Well, what is going to change? This is going to change. So the relationship between the angle in degrees and the length of arc is not so simple. So this, let's call this delta theta radians. So we're using radian angle. What about delta theta degrees? Okay, delta theta degrees, we know that every 360 degrees is corresponding to a total arc length of 2 pi r. So you take the angle, you divide by 360, and you multiply by 2 pi r. That effectively converts the angle into the arc. So to find the arc length, you're going to take the delta angle in degrees, and you multiply 2 pi r, you divide 360 degrees. So this is the same as delta theta degrees times r, and now you have a 2 pi over 360 degrees conversion factor. See here, this is pretty much right here, right? Delta s is equal to r times delta theta, no conversion factor or factor of 1. And here, delta s is delta theta in degrees times an r, and then this conversion factor. So this basically tells you using radians is much easier to describe rotational motion and also relationships between rotational and translational motions. And just as an added bonus, so let's talk about this trigonometric functions. So we have a pretty shallow angle here. Okay, so here we have a very shallow angle. We'll call it theta, and we have, this is the opposite, this is adjacent hypotenuse. So we know that sine theta is equal to opposite over hypotenuse. So what if I say that this is a pretty small angle? Instead of using the opposite, I can imagine extending adjacent for a little bit until it is as long as the hypotenuse, and then just stretch an arc of a circle around that. So this is delta s. Well, we know that delta s is slightly longer than the opposite, the O. So let's put O here and move that away, and maybe even move that down here. Okay, so we know just from looking at it, delta s is longer than O. But if you imagine closing down the angle to a much smaller amount, then delta s is very close to the O, right? So if we imagine that this angle is much less than 1, we're actually using 1 radian. Alright, so much less than 1, then this s, delta s is approximately equal to the opposite. This is the opposite, not the 0. Okay, not 0. Okay, so what does that give us? So sine theta now is approximately equal to this opposite delta s, or this h, and this h turns into an r. So these are now both radii, right? So we know what that is, an arc length over radial length. That is actually the theta. So now we have sine theta approximately equals to theta. So this is when theta is much less than 1 radian. So I can give you an example. For example, 0.1, say theta equals 0.1 radians. And that is equivalent to, according to that, right, 5.73. So 5.7 degrees. So about 5-6 degrees. It's not very small. It's kind of small, but not that small. So now we have this. What is sine 0.1 radian? Or sine 5.7 degrees. Okay, that is approximately just 0.1, because this is the angle in radian, and this is that angle again. See, angle in radian, take the sine function. Well, it's just the same as not taking the sine function. Oops, here, right here. So this. So this makes it easy to approximate. Actually, besides sine theta, as we see, this line here, the adjacent, is also very close to the hypotenuse if you have a very small angle. So that also makes this fraction tangent theta, which is the opposite over adjacent, approximately equal to theta itself. So basically we have sine theta equals approximately tangent theta approximately equal to theta itself. So this makes it quite easy to estimate small angles, sine or tangent, and in much of physics and engineering, we call this small angle approximation. A lot of motion can be easily solved using this small angle approximation. And what is small angle? Well, that is in terms of radian. Much less than 1 radian is a small angle. Thanks.